Black holes. You know, in our culture, they're basically the ultimate cosmic villains. These voracious voids that just swallow stars, planets, anything that gets too close. They're always painted as these terrifying engines of pure destruction. But how much of that is just good science fiction and how much is actual science? Well, let's dive in and really try to separate the cosmic myth from the quantum reality.
So let's tackle the biggest myth right off the bat. This idea that black holes are like giant vacuum cleaners for the universe, just relentlessly sucking everything in. I mean, it's a really powerful image, right? But is it actually correct? The short answer? Not even close. And the reason why gets to the very heart of what gravity really is.
You see, it all comes down to the fundamental physics. A vacuum cleaner literally works by creating a pressure difference. It actively pulls stuff in. Gravity, on the other hand, just doesn't work that way. It's an attractive force between any two things that have mass. It's not sucking anything, it's just a pull, and how strong that pull is depends entirely on how massive the objects are and how far apart they are. That's it.
Okay, to make this crystal clear, let's do a little thought experiment. It's a famous one. Imagine right now our sun just, poof, vanishes. And in its place, a black hole with the exact same mass appears. What do you think happens to Earth? To all the other planets? Are we all just instantly doomed, pulled into the abyss?
The answer, and this might surprise you, is absolutely nothing. Gravitationally, at least. Our orbit wouldn't change at all. And this just perfectly illustrates the point. From way out here where we are, it's the sun's mass that keeps us in orbit, not what it's made of or how big it is. We just keep on orbiting that one solar mass black hole like nothing ever happened. Now, yeah, it would get very, very cold and dark, but we wouldn't get sucked in.
So you're probably wondering, if they don't suck, why does anything fall in? Well, the key is you have to get incredibly close, and even then it's not automatic. You have to lose your orbital energy. For gas and dust, this happens in what's called an accretion disk. It's this swirling traffic jam of matter where particles crash into each other, creating tons of friction. That friction heats the material up to millions of degrees, making it glow incredibly brightly. You know, that's actually the light we see from black holes. It's the final fiery scream of matter before it takes the final plunge.
Okay, so we've busted the whole cosmic vacuum cleaner myth. But the story gets so much more interesting. It turns out black holes might not just be the universe's demolition crew. In a really strange, counterintuitive way, they can also be creators. This question, it really challenges everything we think we know about them. We picture them tearing stars apart, right? But what if these engines of destruction could actually set the stage for new stars to be born? A pretty recent study in the journal Nature suggests the answer is a big, surprising yes. So how on earth does this work? Well, a supermassive black hole at the center of a galaxy can shoot out these ridiculously powerful jets of gas. You'd think that's just pure destruction. But what happens is, these outflows carve out these huge, low-density bubbles in the space around the galaxy. And then, when a smaller galaxy happens to wander into one of these bubbles, it's like it's entered a protective shield. It's suddenly safe from these harsh intergalactic winds that would normally strip away all its gas. And inside that cocoon, the little galaxy can keep its gas and happily churn out new stars. The destroyer becomes a protector.
How wild is that?
And that creative role might actually be super important, because not every galaxy has one of these giants. While something like 90% of huge galaxies like our own Milky Way have a supermassive black hole, only about 30% of the smaller dwarf galaxies do. And that difference gives us really important clues about how these monsters form in the first place, suggesting they kind of have to be born big, right in the crowded centers of massive galaxies.
All right, we've talked about what a black hole does from a distance. Now, let's get up close and personal. Let's journey to its most famous and most misunderstood feature, the boundary that really defines what a black hole is.
This is it, the event horizon. And it's not a physical surface you could, touch or crash into. It's way weirder than that. It's a one-way door in space-time itself. Once you cross it, every possible path you could take leads to the center. Escape becomes impossible, because to get out, you'd literally have to travel faster than light. And, well, you can't.
But for a black hole that's spinning, and most of them are, there's another, even stranger region just outside the event horizon. It's called the ergosphere. And here, the black hole's rotation is so powerful, it literally drags the fabric of space-time around with it. This whole effect is called frame dragging, and it's so extreme that inside the ergosphere, you are physically forced to move. Standing still is not an option, it is literally impossible.
And there are so many myths about this boundary. First off, you don't magically hit the speed of light when you cross the event horizon. From your point of view, you're just falling. Second, this popular idea that space and time literally swap roles on the inside, that's a mathematical quirk. It's an artifact of one specific way of drawing the map of spacetime, not a real physical switch. And finally, the ergosphere isn't some surface of infinite redshift, it's a whole volume of space where spacetime itself is being forced to move.
So, we've crossed the boundary. Now we're going to journey into the deepest mystery of all, right to the very heart of the black hole, to a place where our current laws of physics just completely fall apart.
Our best theory of gravity, Einstein's general relativity, it predicts that at the center of a black hole, all of its mass gets crushed into a point with zero volume and infinite density, a singularity. But here's the thing about infinities in physics. As Christopher Baird points out here, they don't really exist in the real world. An infinity is basically a giant red flag telling you your theory is broken. And this analogy is just perfect. Imagine a simple model of a guitar string predicts that if you play it just right, it will vibrate with an infinite amplitude. Does that happen? Of course not. In reality, the string snaps. The infinity just told you where your simple model failed. A black hole singularity is the exact same thing. It's the place where general relativity snaps and screams at us that we need a better, deeper theory. We need a theory of quantum gravity.
And that leads us, finally, to the ultimate puzzle. This is a deep, profound conflict between the two pillars of modern physics, general relativity and quantum mechanics, and it's a puzzle that has been baffling scientists for decades.
So you've got this epic showdown. On one side, you have quantum mechanics, and it has a fundamental, unbreakable rule. Information can never be destroyed. It can be scrambled, hidden, rearranged, but it's always there. On the other side, you have Stephen Hawking's work, which showed that black holes aren't forever. They slowly leak energy and evaporate. But this leakage, known as Hawking radiation, it seems to be completely random thermal heat, carrying no information out at all. See the problem? If the black hole disappears, where did the information of everything that fell inside it go?
The way this radiation happens is just fascinating. It turns out that so-called empty space is actually this fizzing brew of virtual particle-antiparticle pairs that pop into existence for a split second and then disappear. But if a pair gets created right on the edge of an event horizon, one can fall in while its partner escapes. That escaping particle carries energy away, which means the black hole loses a tiny bit of mass. To someone far away, it just looks like the black hole is faintly glowing.
And this brings us right back to that massive, universe-breaking question. If the black hole just radiates itself away into a featureless, random glow, is all the information about the unique things that made it, the stars, the dust, maybe an unlucky astronaut, is all of that just gone forever? Wiped from the universe? Because if it is, that would violate the most fundamental rule of quantum physics. The modern thinking on how to solve this paradox is incredibly subtle and really mind-bending. It suggests that the information isn't lost, and it's not even hidden inside the black hole anymore. The trick is that we've been asking the wrong question. It's not where the information is, it's how it's stored. In the relationships, the correlations between different parts of the whole system. So here's the big idea. When the black hole is young and big, the information about what fell in is stored in the quantum entanglement between the stuff inside the black hole and the Hawking radiation that's just starting to come out. But as the black hole evaporates and shrinks past its halfway point, a kind of switch happens. That same information gets transferred. It's now encoded in these incredibly subtle correlations between the radiation that came out early and the radiation that's coming out late. The information gets out, not in any single particle of radiation, but in the intricate pattern connecting all of them across time.
So in the end, black holes aren't the universe's ultimate erasers. They're more like cosmic hard drives that take information, scramble it completely, and then slowly, painstakingly release it back out in this fantastically complex, encoded message. They represent this incredible frontier where gravity and quantum mechanics finally meet. And what they're teaching us is that the story of our universe isn't just written in things, but in the deep, intricate connections between them. And the real question is, what other secrets are we going to find when we finally learn how to read that message?